That's not a pitch issue.
Would it fade?
Would not fade, no.
Make your ears pop?
I hope not. Oh,
I was just thinking about pressure. Obviously, that's different than sound pressure.
Oh, there it is. Now this can be done with tuning forks. The trouble with tuning forks is that they don't vibrate forever, and so I have to keep recharging it. So I'm going to use this. The downside of this is if this is too loud, you won't hear anything coming from that. And I guess we're going to have a reach issue, but I think I can deal with that. All right, give it a chance to come up. Now, when I do this lab with students, nothing to see there. There are sometimes these false harmonics that come into it, and if you get one of the harmonics wrong, it really messes up the rest of the experiment. So there's going to be a certain amount of knowing what the answer is and targeting it. So let's talk about the first harmonic while the lab quest is still heating up, or warming up, or booting up. If I do a 400 hertz so if my wavelength is 400 hertz, what would the wavelength be? That's my frequency. How would I find the wavelength? What would I need to know besides the wavelength? If I do time, that like time for what? I could find the period. The period's going to be 0.0025 seconds. How does that help us? Sorry? It was written on the board over here.
The speed?
Yes. If I know the speed of the sound wave, I can figure out what the wavelength is supposed to be. So what is the speed of sound? Approximately. You said 300 something, and then you said never mind? Is that what you said?
I said 3 times.
Oh, 3 times?
I was going to say speed of light.
Oh. Speed of light is somewhere around 1 million times faster than the speed of sound. All right. Now the speed of sound does depend upon the temperature of the air. Now, I'm not measuring the temperature of the air right now, so I'm just going to go for sort of a ballpark. It's somewhere around 340 meters a second. So this is speed of sound. So I wanted you to say 300 because I figured you were close to it. So if the speed of sound is 340 meters per second, I know that's equal to the frequency times the wavelength. And my frequency is going to be 400 hertz times my wavelength. So the math problem I'm dealing with here is 340 is equal to 400 times the wavelength. That's the math problem. So what is the wavelength? Units?
Meters.
All right, so the wavelength. So in other words, if I hit the 400 hertz note, that wave is going to travel that far before the next wave is created. Now let's figure out what L needs to be in order for us to hear that first harmonic. I know for the first harmonic, L is a quarter of the wavelength. So for the first harmonic, L is equal to 1/4 of the wavelength. So that's 1/4 of 0.85 meters, which is 0.2125. Okay, meters. So in order for us to be able to hear that we are on the first harmonic, I would expect the air column to be 21.25 centimeters tall. Right now, the water is at about 17 centimeters on the tape. For some reason, and I have not figured out why, I thought I had a clue at some point, but I don't know why they did it. The tape, 0 on the tape begins 2 centimeters below the top. So whatever number's on the tape here, we have to add 2 centimeters. So the tape says around 17 centimeters right now. It's actually 19 centimeters from the top. I want L to be 21 centimeters, a little more than 21 centimeters, so that's going to be around, on the tape here, somewhere around here. That should be the water level when we hear the first harmonic. Start the water up a little bit so that you can hear the progress. Auto. That's 1,000 hertz. All right, 400 hertz. We can check the video later, but I nailed that, didn't I? All right, so let's see, the speaker is there. That's right. Now we're going to run into that issue, so I'm going to drop this down. There's the speaker. Yeah. Okay, so it's going down, hitting the surface of the water, and then bouncing back up. I assume you heard something there. So what happened when we passed by that first harmonic?
I went shrill a little bit, like it went higher, like the sound.
A higher frequency?
Yeah, but it changed. I don't know what it changed.
Okay, it changed. It should have been a little bit louder. That's how you tell what a harmonic is, by when, because it's soft sound. And let me drop this down to perhaps that it's not quite as, this is not quite as shrill. That actually is the first harmonic right there. So what the antinode represents, it's the biggest difference in pressure. So for your eardrum, it's pushing it in and pulling it out farther, and we sense that as a louder sound. That's what I was hoping to achieve there. Now there was another point right below that where it was louder, so you got that, it almost was like a change in tone, but there's definitely a difference in the quality. And then it got then further down it got louder. That's one of the false harmonics. And so that's why the lab, it should be the only lab where Massason and I would both go figure out what it's supposed to be and then do the measurement there. Because if you consider that what I'm claiming is the first harmonic is the first harmonic, and then the next one is the second harmonic, if you're actually trying to find the speed of sound, it is completely wrecked at that point if you get one of those wrong. So third harmonic, let's figure out what that needs to be. Well, that hasn't changed. That hasn't changed. So my wavelength is not changing with 400 hertz. Third harmonic, I know that L is 3/4 of that. So it's 3/4 of 0.85. 0.6.
37.
Oh, by the way, it is that first harmonic was at around 18 centimeters, and we had predicted, 18 plus the 2 was around 20 centimeters, and we predicted 21, so we're about 5% off. Let's see how close we get now. Now, a fun thing about this, if I take this thing down too far, the reservoir will fill up and spill over. I generally recommend you have a trash can nearby in case you need to dump water quickly. I don't think it's going to dump at that distance. But there's chances I can just balance it. And it will stay balanced. Close to 0, apparently. Not my worst water accident in a class. Really? All right, well, that's booting up again. I think the first time I taught 110, I was doing the cable call out from underneath the water, the glass with the water. I did not do that particularly successfully. That's the worst water accident. All right, well, that's booting up. 2 free ends. We'll just jump ahead just a little bit, and then we'll jump back. 2 free ends. Basically, I need 2 open surfaces. This was a free end. This was open here. So I need something like this, where I have 2 free ends. As I swing it around, and for reasons we'll explain it later, first harmonic is somewhere around there. Yeah, you hear that? That's the second harmonic. Third, fourth, fifth, and I think there's a little bit of a sixth in there. So we're actually only hearing the harmonics on something like this. And so what we're going to do is we're going to end up with predictions about what those harmonics are going to be and see how close we get. And this is up again. Drop this back down again. 30. And at 400 hertz. All right. We just passed the third harmonic. Right there. All right, and that was about 61 centimeters on the tape here, plus the 2 centimeters for the manufacturer, and puts that at 63 centimeters, and we predicted 63.75. So hopefully it's at least some evidence that what I'm telling you has some truth to it. Questions to hear before we actually do the analysis for the 2 free ends? And we'll find out who has good hearing. So with 2 free ends, are they going to be nodes or antinodes? The simplest pattern we can have basically that. How many waves is this? So L is equal to a half of a wavelength. This is the first harmonic. Let's just go ahead and make our prediction right now of L. L is the length of the dupe. So pull out the handy dandy meter stick and just measure it. I'm going to straighten it out some. And it will stretch some as I spin it. I'm just going to give it a little bit of a stretch here. Not significantly, and it's 83 centimeters. So L, 83 centimeters, which is 0.83 meters. Therefore, what is the wavelength? Or how would you find the wavelength? A couple of people hitting calculators here, so I'm assuming somebody's going to give me an answer. Unlike what we did before with that, we don't know what the frequency is. We're trying to figure out what we're trying to find the frequency this time.
Is it okay to convert it, 1/2 into 0.5 or
Sure.
Okay, so I got 0.415 then.
Ooh, okay, I see what you did. So the math problem we're working with, we're trying to find the wavelength. And we know L, so it's 0.83 is equal to 0.5 times the wavelength. So you end up dividing by 0.5.
Where does that 0.5 come from?
That's a half a wave.
Oh, her. Oh.
1.66.
1.66 meters. All right, so now what is the frequency that we should be hearing for the first harmonic? And by the way, for the purists out there, what I said potentially was nonsense. Because technically you don't hear the frequency, you hear the pitch. Just to let you know, I use pitch and frequency interchangeably. And you know what, childhood scars. You can only overcome so many. If you're not a purist, then just go with it. So how would we find the frequency now that I know the wavelength? While you're trying to figure that out, let me see if I can actually get sound out of this thing. This is going to be better than the LabQuest. You can hear that, right? Here's the other one. All right, so what's the frequency that we should hear?
204.82 hertz.
204.8? How'd you get that?
I divided 340 by 1.66.
Yes. We're using this formula right here. The speed is equal to the frequency times the wavelength. This time we know the wavelength, 1.66 meters. We divide by it and we're left with the frequency. What are the units here?
Hertz.
Yes. So, because this does not do decimals for frequency, I will round that off. So 205, 205. Barely hear that. I got the volume up. All right, so let's do it this way.